Is the screen visible? Okay. So in the last class, we have finished our discussion on the depletion type MOSFETs. So as of now, actually, we have done two type of FETs. The first type of FET was the junction FET, that is the JFET, and the second type of FET was depletion type MOSFET. And if you recall, the difference between both of them was that the JFET will work only with gate to source voltage less than 0, whereas the depletion type MOSFET can work both with VGS less than 0 as well as VGS greater than 0. So when VGS is less than 0, it is set to work in the depletion mode. And when VGS was greater than 0, it was set to work in the enhancement mode. And also in the enhancement mode, the drain current which was observed in the depletion type MOSFET was greater than the maximum saturation current, that is IDSS. So this was a brief summary of FETs that we did so far. Now today we are going to start with the enhancement type MOSFET. So these type of MOSFETs, they are basically similar to the depletion type in the construction, but their operation and the characteristics are slightly different. So one more thing I want to remind you, like in the previous class, we did a few questions on the depletion type MOSFET, and we said that as far as doing questions is concerned, there is no difference if we consider a depletion type MOSFET or a junction FET. But this is not true for the case of enhancement MOSFET, because here we have different equations. So whenever you have any question related to the FETs, you need to first see if it's a depletion type MOSFET or a junction FET, in which case you can apply same set of equations, or if it is an enhancement type MOSFET, then you have to choose different type of equations. Okay, so with this we begin. First we are going to see the basic construction as is shown over here. So as you can see here also, so this is, we are talking about N channel. N channel, P channel are complementary. We know that, just that N is replaced by P and P will be replaced by N. And for solving the circuits, the polarity of the voltages get reversed and the direction of currents also get reversed. Other than that, all the concepts remain the same. So here, while we are talking about the N-channel enhancement MOSFET, we see that just like the case of the depletion type MOSFET, here we have a slab which is made up of a P-type material, and we call this slab as the substrate. And this actually acts as a foundation on top of which other components of the FETs are fixed and the final setup is prepared. So then this substrate over here, the P-type substrate, it could be connected to the source, in which case this is a 3-terminal device for which the circuit symbol is going to look like this, or the other option is it could remain open. Then in that case, this would be a 4-terminal device. But we are not going to consider this case. So for the sake of simplicity, we will assume that the substrate is actually shorted to the source. Then besides the substrate, we have our usual terminals, the drain, the gate, and the source. So you see over here, the drain and the source, they are connected through the metallic contacts. So these black boxes are the metallic contacts. So through the metallic contacts, they are connected to these heavily doped N regions. But the difference with respect to the depletion type MOSFET is that here we do not have any channel, whereas in case of depletion type MOSFET, we had a channel which was connecting these two N-type regions. But here we do not have any channel. So that is the very basic difference between the construction of a depletion type MOSFET and an enhancement type MOSFET. Then the gate, this is connected through an ohmic contact, and there is a dielectric layer SiO2 which keeps this gate insulated from the p-type substrate, just as we have seen for the depletion type MOSFET. So this is my basic construction. If you look at the symbol, so the difference in the symbol is that here you show this dotted line over here instead of solid line. So if you remember earlier, we had a solid line this way. But now we have this dashed line, and this dashed line actually symbolizes the absence of the channel. And since this is N channel, so we have the arrow pointing inwards. If it was a P channel, then we would have an arrow pointing outwards. So this was the construction. Now let us see how does this operate. So we are going to first consider the case where VGS is equal to 0 and VDS is greater than 0. So this is the first condition which we have considered in each of the transistor we have studied earlier. So if VGS is 0, that means gate and source, they are short circuited such that there is no potential difference between them. And this is a 3-terminal device, so supposedly the substrate is also shorted to the source, and between the drain and the source you apply some positive voltage. This would be something like this. So here we will apply VDS, which may have some positive value, and here we have no voltage because gate and the source are shorted. So now you see here we have the positive terminal of the voltage that we have applied. So this positive voltage, what it will try to do, it will try to pull out the electrons from these N regions, and it will try to create a drain current. But we see that here there is no channel. So therefore the path of this circuit is not complete. So in this situation, effectively the drain current is going to be 0. So what has happened? Because there is no channel, it will be like this device just consists of 2 reverse bias PN junction. First is this one and other is this one. And since there is no path connecting these 2 N type of regions, so no current is able to flow through this device. So in this case, we have the drain current equal to 0. So this is another very important difference when you compare the working of the depletion type MOSFET and the enhancement type MOSFET. So if you remember, in case of depletion type MOSFET, when VGS was equal to 0 and VDS was greater than 0, that time we have the maximum saturation current flowing through the transistor, and we denoted this as IDSS. But here there is no current because there is no channel. So now to initiate the current, what we need to do is we need to apply some positive voltage over here. So next what we do is we are going to apply some positive voltage over here. So this is my second condition where I am saying that my VGS is greater than 0 and my VDS is also greater than 0. तो देखो अब यहाँ पे VGS पॉजिटिव लगाया तो क्या हुआ, this substrate, this was also p-type substrate, and here you have applied a positive voltage. So what happens, this positive voltage tries to repel the holes which are the majority carriers in this p-type region further back into the deeper p regions, and in turn it attracts the electron towards this insulating layer. So kya hua? Because this was positive, this is also positive. So this will try to repel the holes away and in turn attract the electrons which are the minority carriers in this p-type region. So now if you go on increasing the value of VGS, this accumulation over here, this keeps on increasing. So the accumulation of electrons, this keeps on increasing, and this increases until you have the gate source voltage greater than or equal to some threshold value VGTH. Sometimes this is also denoted as V threshold, that is V small t. तो जब तक ये VTH तक नहीं बढ़ जाएगा तब तक यहाँ पे इलेक्ट्रॉन्स accumulate होते रहेंगे. And once this threshold voltage is reached, then this accumulation is actually good enough to support a flow of current into this transistor. So now the electrons, they can move out from the drain towards this positive side, thereby creating the drain current to flow from the drain to the source. So this is my flow of electrons, and this will be the direction of flow of current. So what we saw just now, we saw that if we increase the value of VGS, some electrons are attracted, and if VGS is large enough so that it is crossing some threshold voltage, then in that case, a channel is induced. A channel is induced, and this channel is then capable of supporting the flow of current into the device. This induced channel, sometimes it is also known as the inversion layer. Inversion layer. And also observe that this is only possible when VGS is positive. If VGS was negative, then again, due to the absence of channel, no current could be supported. So if VGS is less than 0 or VGS is equal to 0, in these two conditions, we do not have any drain current in this device. So we say that this device works only in the enhancement mode. This device works only in the enhancement mode. Why? Because when VGS was less than 0 or when VGS was equal to 0, at that time, the channel was not existing. And once you started increasing VGS such that it crossed some threshold, it was such that a channel is induced, which we also called as the inversion layer, and that channel then supported the flow of electrons in this region. So since this device, this can work only in the enhancement mode, therefore this type of FET is known as enhancement type FET. Whereas depletion type में क्या हो रहा था? Depletion type could work both in the enhancement mode also, where it was increasing the drain current beyond IDSS, and it could also work in the depletion mode, where VGS was less than 0 and VGS was greater than 0. So since this is more general case, you call this as the depletion type. और यहाँ पे तो एक ही मोड सपोर्ट हो रहा है, therefore this is known as the enhancement type. So this was when we applied some VDS and we were increasing the value of this gate to source voltage. Now there is one more possibility. What possibility is that? मान लो हमने VGS को increase किया and we increased VGS such that now VGS has become greater than the threshold voltage. And now what I do is, once this condition is met, then I keep VGS as fixed, and instead of increasing VGS further, I start increasing VDS. तो फिर क्या होगा? So then this type of situation happens. So what's happening over here? Once we have VGS as constant and I keep increasing the value of VDS, then what actually happens is that your saturation, your drain current initially increases and then later on it saturates. So this behavior is similar to the behavior that you have seen earlier in case of depletion type MOSFETs. तो उसमें भी क्या था, जैसे हम जब output characteristics plot करते थे, on the x-axis I had VDS, on the y-axis I had the drain current. So you remember the shape was like this. That means with increase in VDS, initially the drain current increased and then eventually the drain current saturated to some value. So this is also happening over here. So वहाँ पे ये किस वजह से हो रहा था? वहाँ पे ये pinch off की वजह से हो रहा था. So here also similar condition happens, which we call as pinch off, but थोड़ा सा difference है. So let us try to understand why this flattening of the curve is happening. For example, say that हमने VGS की value ली है 8 volts. So I'm trying to explain this by taking an example. So say we have taken VGS is equal to 8 volts. And this is well above the threshold voltage, because generally threshold voltage is on the order of like 1 or 2 volts. So that means clearly this is sufficient to induce. Let me say that initially my value of VDS was 2 volts, and later on I increased my value of VDS from 2 volts to 5 volts. तो जब VDS की वैल्यू 2 volts थी, at that time if I want to see how much is the effective voltage which is appearing across the gate and the drain, यहाँ पे कितना voltage आ रहा है, this voltage is VGD. So how much voltage this will be? This is equal to VGS minus of VDS. So this is 8 volts and VDS I have applied as 6 volts. Whereas for the other case, this will be 8 volts minus 5 volts, so 3 volts. So what does this mean? This means that when I increase the value of VDS from 2 volts to 5 volts, I'm actually reducing the effective voltage that is appearing between the gate and the drain. And once the voltage over here reduces, that means the force which was being exerted over here, jiski wajah se holes were pushed inside and electrons were pushed towards or attracted towards this silicon dioxide layer, this force also reduces with the reduction in VGD. VGD reduces, the electric field also reduces. So with the reduction in electric field, now you do not have many electrons in this region such that the channel could conduct the current at the same rate as it was conducting earlier. So this effectively causes the induced channel to taper down in the width in this manner. So this situation over here, we are calling this situation as the pinch-off situation. And just not to get confused by this terminology, pinch off does not mean that the channel is going to go away completely. Rather, we will say that a very narrow channel still exists, which is going to just support the current which was achieved until this tapering happened. So because of this tapering, now we have high density, almost constant current flowing through the transistor, and this current is the current which we see over here in the saturation region. So if I say that what is my condition for pinch off? Condition for pinch off. So the condition for pinch off is that VGD, that is the effective voltage appearing across the gate and the drain, this should be less than VT. Because if the voltage is not as high as the threshold voltage, then sufficient amount of electrons will not be attracted to create a proper flow of current into the device. So this is my condition. Is condition say we can further derive the condition in the form which we are more familiar with. So this will be VGS minus VDS is less than equal to VT, or you can say that VDS must be greater than or equal to VGS minus VT. So in this, under this situation, your transistor will be in pinch off. That means the current will be saturated, or you will say that the transistor is working in the active region. So if you compare this condition with the condition that we see in case of the depletion type MOSFET, तो वहाँ पे VT की जगह it was VP, that was the pinch off voltage. So here we do not call this term as the pinch off voltage, rather we call this as the threshold voltage. And this threshold voltage is the minimum gate to source voltage that has to be applied in order to induce this channel between the two N-type regions. So this is my active region, and the condition where this is equal to this. So for example, I say that VDS is equal to VGS minus VT. That means my transistor is just entering into the saturation or the active region. Therefore, this is also known as VDS saturation. So this is the condition for active region. Likewise, if I want to see the condition for ohmic region, then we know this is pretty straightforward. VDS will be less than VGS minus VT. just as the previous cases. And what about cutoff? The cutoff situation is if VGS is less than the threshold voltage, that time the transistor will remain cut off. So these are the three regions of operation. The regions of operation are same. The condition is also somewhat same. Just the difference is between VP and VT. But what will now differ is the equation of the current. So here we see both the drain characteristics as well as the transfer characteristics. So let us first see the transfer characteristics. So we recall that transfer characteristic is actually a plot between VGS and ID, where VGS is what? VGS is the input voltage, whereas ID is the output current. And now because we understand the behavior of the enhancement type MOSFET, we know that until VGS has reached some threshold, the current will be zero, and beyond that, the current is going to increase. And this increase in current is governed by this equation. So if the transistor is working in the active region, this is my equation for the drain current. If you recall, for the case of the depletion type MOSFET, this was ID is equal to IDSS into 1 minus VGS by VP whole square. ये इक्वेशन था किसके लिए? डिप्लीशन टाइप के लिए. But for enhancement type, the equation is ID, that's equal to K into VGS minus VT, where this K is actually a constant which depends upon the fabrication parameters of the device. Take. Okay, so now if we see the drain characteristics. So drain characteristics में let us try to verify the concepts that we have studied so far. पहला concept क्या पढ़ा? पहला concept ये था कि if I increase the value of VGS, the drain current is going to increase. So that's what we see over here. So VGS is 4, then 6, then 8, then 10, and so on. So as you increase the value of VGS, the value of drain current also increases. This is the first observation that we confirm. Second observation was what is happening with respect to the drain to source voltage. So we see that with increase in the drain to source voltage, as you increase VDS, ID increases, and then eventually it enters into the saturation. So this is the second condition which we have validated over here. The third thing that I want you to observe is as we are increasing the value of VGS, the saturation voltage is also increasing. So for example, when VGS was 4 volts, at that time, around this voltage, that means VDS is equal to 2 is where the drain current is saturating. But now if you increase VGS from 4 to 6, then the saturation voltage is now moved to a greater value because this is now around 4 volts. Then similarly, if you go for 8, the saturation voltage is further increasing to say 6 volts and so on. So that means with increase in VGS, we are actually also increasing the saturation voltage, VDS saturation, and in turn, we are also increasing the drain current. So this dotted line or the locus of this curve, which shows the movement of VDS saturation, this demarcates the active region and the ohmic region. So towards this side, we have the condition VDS is greater than VGS minus VT, and towards this side, we have the condition VDS is less than VGS minus VT. So this region is known as the ohmic region, and this region is known as the active region. So once again, we recall this is known as active region because here the device can work as an amplifier. And this is ohmic region because in this region, the device can act as a variable resistor. And what happens when VGS is equal to VT? So if I say that VT is equal to 2 volts, because typically it is on the order of 2 volts or 1 volts or something like this. So you see that over here, this line is almost overlapping with the horizontal axis. So here, this region over here where the drain current is 0 and VGS is less than or equal to VT, this region is known as the cutoff region. Okay, then the equation of current. So this equation we have already seen. This is the equation that holds true for the case of enhancement type MOSFET when the MOSFET is working in the active or the saturation region. Whereas this equation over here, that is ID is equal to K multiplied by 2 times of VGS minus VT into VDS minus VDS squared. This is the equation which holds true for the enhancement type MOSFET when it is working in the ohmic region. So we can have one approximation over here. For example, if I say that the value of VDS is very small, if VDS is very small, then this quadratic term can be ignored. And in that case, I can write that the drain current is simply equal to K times 2 VGS minus VT multiplied by VDS. And in this situation, if I also have to find out the output resistance, that is RDS, so this will be equal to VDS by ID. So you can substitute ID ये है, VDS ये है, तो VDS will get cancelled and this will become simply equal to 1 divided by K 2 times of VGS minus VT. This is my output voltage. Any doubt as of now? No? Okay, so if there are no doubts, then I think we have all the concepts that are required for doing the question. So we will quickly see 2 questions and close for the day. So this is the first example. This type of circuit we have already seen in case of the depletion type MOSFET also, as well as for the JFET also, but just that because the equations are different, so we are going to see this again. So what does the example say? It says that from the characteristics of N-channel enhancement MOSFET, suppose it is determined that in the active region, when VGS is 8 volts, then ID is approximately 9 milliamperes. So just pay attention to the language which is written over here. तो यहाँ पे ये नहीं कह रहा है कि इस device के लिए VGS is 8 and the current flowing through the device is 9. No, it is not saying like this. What it is saying, it is just giving a condition that if VGS is 8, then ID is 9 and the transistor is working in active region. So this condition is actually given in order to find out the value of the constant K. क्योंकि एक्टिव रीजन में हमको पता है, एक्टिव रीजन में ड्रेन करंट की क्या इक्वेशन होती है, दिस इज इक्वल टू ID K टाइम्स ऑफ VGS minus VT whole square. So if VGS value is known and ID value is known, K can be calculated. So using these these values, 8 volts over here and 9 milliamperes over here, substitute करके K की value निकाल ली है 0.25 milliamperes per volt square. Now further, when we have this value of K, it is saying that VT is given as 2 volts, which is fine, and VGG is given as 10 volts. So if you observe the circuit over here, because there is no resistance connected to the source terminal, that means we understand from here that VGS is actually equal to VDD, which is given as 10 volts. And then what it is required to find? It is required to find ID and VDS for two cases. In the first case, when RD is given by 250 ohms, and in the second case, when RD is given by 1 kilo ohms. So let us start with the first case. अब यहाँ पे when RD is 250 ohms, so how do we start? We start afresh. We say that we don't know in which region the transistor is operating. So let me assume that the transistor is operating in the active region. And if the transistor is operating in the active region, then I know how to calculate the drain current, because this is equal to ID K times of VGS minus VT whole square. And here K value I have just found in the first step. This is 0.25 milliamperes. VGS की value मुझे पता है from the circuit. VGS is 10. So you have to keep in mind that VGS is 10 and not 8 as given over here, because this value was just to find out the value of K. From the circuit, VGS is taken as 10 and VT value is also given. So if you substitute all these and if you solve, you are going to get ID as 16 milliamperes. And if ID is 16 milliamperes, how about VDS? So VDS निकालने के लिए what we do? We apply Ohm's law over here. So we say that ID is equal to VDD, which is 16 minus VDS, which we have to find out, divided by RD, and RD value in the first case is 250 ohms. So if you substitute ID as 16 milliamperes in this and then calculate the value of VDS, you're going to get VDS value as 12 volts. So now we don't have to stop over here. कि VDS निकल गया तो सब हो गया. The last step is to verify if this is in conformity with the assumption that we have taken, because these values are calculated based on assuming that the transistor was working in the active region. So for that, what is the condition? The condition is that VDS has to be greater than or equal to VGS minus VT. तो यहाँ पे VGS minus VT कितना होगा? VGS is 10 and VT is 2, so this is equal to 8 volts. So since 12 volts is greater than 8 volts, we say that the active region assumption is correct. Therefore, the final answer to this question is ID is equal to 16 milliamperes and VDS is equal to 12 volts. Now, we see the second case where we have changed the value of drain resistance from 250 ohms to 1 kilo ohm. So in that case, what happens? Again, since we are not sure about which region the transistor is operating, we start by saying that let the transistor be operating in the active region. So if the transistor is in active region, then I know that drain current will be given by this formula. Here RD is 1 kilo ohm. So since RD is not even appearing in this formula, that means this is going to remain same as 16 milliamperes. And then based on this, if I have to calculate VDS, then VDS will be VDD minus the voltage drop that is happening across the resistance RD. This is the same equation that you obtain by applying Ohm's law over here. So this becomes how much? VDD is given as 16 minus ID is 16 milliamperes and RD is 1K. So this is equal to 0 volts. Whereas what was the value of VGS minus VT? This was equal to 10 minus 2, that means 8 volts. So now 0 volts is actually less than VGS minus VT. That means this active region assumption was wrong, and therefore we will change the assumptions and say that let my transistor be now operating in the ohmic region. So with this assumption, अब ohmic region में मान लिया है, तो what will be the new drain current? New drain current will be given by K times of 2 VGS minus VT multiplied by VDS minus VDS square. So here ID is what you have to calculate. VGS value is known. VGS is equal to 10 volts and VT value is also given. and VDS is unknown. So here there are two unknowns, ID is unknown and VDS is also unknown. So let me substitute the values. This will be ID is equal to 0.25 milliamperes into 2 times 10 minus 2 is 8 multiplied by VDS minus VDS ka whole square. So let me say that this is my first equation. So based on the characteristics of the enhancement type MOSFET, I wrote this equation by using the standard formula. The other way of writing the drain current equation is through the circuit. So if you see through the circuit, we know that the drain current is equal to 16 minus VDS by RD. So that's my second equation for the same variable. This is equal to 16 minus VDS by RD, and RD in this case is 1 kilo ohms. And then because both of them are the equations of the drain current, what I'm going to do is I'm going to equate both of them and do some rearrangement so that I obtain a quadratic equation in this variable VDS square. So that calculation I'm not showing, you can do that and verify later on. I'm giving the final equation. This equation will be VDS square minus 20 times of VDS plus 64 is equal to 0. So from here you will get two values of VDS. So first value is 4 volts and the second value is going to be 16 volts. So which value to choose? Remember, all these calculations we have done by assuming that the transistor is in ohmic region. So we need to choose that value of VDS which is less than VGS minus VT. VGS minus VT was 8 volts. So इसमें से this value is less than 8 volts. So the final value over here will be 4 volts. And when this is 4 volts, you can also calculate the corresponding drain current. This will be 16 minus 4 divided by RD is 1K. So the drain current is going to be 12 milliamperes. ठीक है? Any doubt? Any doubt? अरे नो ही बोल दो.
No, ma'am.
No, ma'am. Okay, thank you for the response. You see, sometimes you also have to understand. कभी कभी मुझे लगता है कि मैं केवल कंप्यूटर से बात कर रही हूँ. Already very few students are coming, and then if you guys don't respond, then it is very disappointing to the teacher. Okay, never mind. So now we see the second question. So what this question says is, we have an NMOS circuit, which is shown over here in this figure. And suppose that VDD is equal to 12 volts. Okay, this is also given. The enhancement MOSFET parameters are given, VT and K is given, and the depletion MOSFET parameters are also given. So that means in this circuit, you have both type of MOSFETs. You have depletion type also, and you have the enhancement type also. Then they say that when V1 is equal to 2 volts, then M1 is in the active region and M2 is in the ohmic region. So what we need to find? We need to find the value of V0, and also we need to confirm the region of operation. So first let us identify which transistor is which one. So इन्होंने यहाँ पे जो symbols use किए, this is actually a bad way of representation, but if you see the standard books, you will see the notation that we have learned. But here for the sake of solving this, ये जो bold वाला transistor है, this transistor is the transistor which is the depletion type of transistor. And this transistor over here is showing the enhancement type of transistor. The bold one is the depletion type and the normal one is the enhancement type. And both of them are N channel because यहाँ पे NMOS circuit दिया हुआ है. Okay. So with this, निकालना क्या है? सबसे पहले देखते हैं, निकालना है V0. So if you look at this circuit, what is V naught? V naught is essentially the voltage drop across the drain and the source of this enhancement type transistor. तो ये निकालने के लिए I know what I have to do. I have to apply KVL over here in this path which starts from VDD until ground. So that means ultimately मैं क्या करूँगी? I will apply this equation that VDD, this is going to get dropped between the first MOSFET and the second MOSFET. Because here there is no drain resistance. Here also there is no drain resistance. So this is the equation that I ultimately have to do, and my variable is VDS1 because this is where V naught is indicated. तो इसको निकालने के लिए ये तो दिया हुआ है. What we have to find? We have to find VDS2. That means we have to find the voltage drop across the drain and source of this depletion type MOSFET first. ठीक है. Now the good thing is they have themselves given that V1 is equal to 2, and when V1 is 2, M1 works in the active region and M2 works in the ohmic region. Where is V1? V1 is actually applied over here. And you see, because there is no source resistance over here and this terminal is grounded, V1 is actually what? This is equal to VGS1. So we have the value of VGS1. So नीचे वाले transistor में, that is the enhancement type transistor which is given to be working in the active region, we can straight away apply this formula that ID is equal to K times of VGS minus VT whole square. Here the value of K is given. This is equal to 0.25 milliamperes. VGS, we just identified that V1 is equal to 2 volts is same as VGS. तो ये value भी दी हुई है. और VT की value भी दी हुई है. This is equal to 1 volts. That means if you substitute everything over here, you will get the value of drain current for the enhancement type transistor. Let me call this as M1. So this is ID for M1. This is going to come out to be 0.25 milliamperes. Sub values rakhi, if you calculate, this will come out to be 0.25 milliamperes. Now, we also know that the drain current for this transistor M1 is same as the drain current for this transistor M2 because gate se to koi current nahi aayega. For each of these cases, the gate current is going to be 0. And there are no resistances in between. So we know that the drain current for M1 will be equal to the drain current of M2. And this is equal to 20.25 milliamperes. So for the transistor M2, now we know the drain current. And if I know the drain current, can I find the value of VDS? Yes, I can find because I know that M2 is the depletion type of MOSFET and this depletion type of MOSFET is working in the ohmic region. So I dig my memory and I see that when a depletion type MOSFET works in the ohmic region, this is the equation of current. So in this equation, what is given and what is unknown? ID तो हमको पता है, अभी हमने previous step में निकाला. This is 0.25 milliamperes. IDSS is given. This is equal to 4 milliamperes, which is fine. 2 into 1 minus. What about VGS? So this VGS is the VGS for the second transistor. So if you observe over here in the circuit, the gate of this second transistor is shorted to the source of the second transistor. That means there is no potential difference between the gate and the source for M2. Therefore, VGS2 is equal to 0. So here we can substitute 0. VT की value already दी हुई है. VDS is what you have to find. So if you substitute the values and simplify this equation will be a quadratic equation in terms of VDS. And if you solve this quadratic equation, you are going to get two values and these values are shown over here, 0.127 and 7.87. But which value we have to pick? So remember, this is about the transistor M2, which is working in the ohmic region. So for ohmic region, the condition on a depletion type MOSFET is that you should choose VDS which is less than VGS minus VP. So VGS for this case is 0, VP is given as -4, so this should be 4. So that voltage which is less than 4 volts is the acceptable voltage. So out of these, we know that 0.127 is the one which is less than 4 volts. So my final answer is that VDS2 is 0.127. और निकालना क्या था, निकालना मुझे VDS1 था, तो मैं क्या करूंगी, ये 0.127 को I will put back in this equation. So VDD was 12, this is equal to 0.127 plus VDS1. So from here you will see that VDS1 is equal to 12 minus 0.1, so this will be something around 11.9 volts. And this is also equal to V0. Okay? One thing we have left, that is to verify if with this VDS the transistor is working in which region. So can you tell me for this case the transistor is working in which region? अच्छा, ये तो region के basis पर ही निकाला था. ठीक है, ठीक है, so that verification is not needed then. Okay, so any doubt in this case? Only thing that you have to carefully use are the equations, and for that you have to give 1 minute to reading the question very carefully कि कौन से टाइप का ट्रांजिस्टर दिया है और किसका क्या पैरामीटर पूछा है. Other than that, there is nothing new. All you have to do is just either use the standard equations for drain current or apply KVL to the circuit diagram. Or sometimes you may have to use the conditions and verify the region of operation. Any doubts?
No.
Okay, so if there are no doubts, then I'll wind up for the day. With this, I am done with the FETs. So in the next class, we are going to start with the op-amps. I think 2 more classes we have, Monday class and Wednesday class. In one of the classes, we'll try to cover as much theory as possible, and then Wednesday ki class mein questions karenge. I think the syllabus for major would be, has the IC posted the syllabus?
Yes, ma'am.
अच्छा, टाइम डोमेन से आ रहा है ना शायद, और earlier
Yes,
than that
ma'am.
also?
Time domain.
Okay. Okay, so from the time domain until op-amp will be the syllabus. ठीक है. So if there are no more doubts, then thank you everyone, and I really appreciate that the exams are so close till you guys are attending the classes. This is a good thing and this is going to help you a lot. क्योंकि जो नया पोर्शन है उसमें से likely the questions will be easier. जो अर्लियर पोर्शन है, जो मिड सेम वगैरह में आ चुका है, उससे हो सकता है डिफिकल्ट क्वेश्चन हो, बिकॉज इजियर क्वेश्चंस हैव ऑलरेडी बीन आस्क्ड. व्हाट अनुराग इज सेइंग?
No, ma'am, he was asking where is the compre syllabus. So,
ओके ओके, ठीक है. हाँ, नालंदा पे होगा कॉम्प्री सिलेबस. ठीक है देन, थैंक यू.
Ma'am, in the
Thank you.
section, within the topic, there is a section called transistor switching times also. So that is not there, right, in the syllabus.
Transistor switching time, in which chapter it is? FET में कि BJT में?
And BJT is actually within the same section. That's why.
ऐसा क्या? No, transistor switching times नहीं है. नहीं, ट्रांजिस्टर स्विचिंग टाइम नहीं है.
Okay.
ठीक है. इट्स ओनली अंटिल, मेरी बुक में दिस इज पेज 362. ठीक है, मतलब जहां तक हम कॉन्फ़िगरेशंस डिस्कस कर रहे हैं.
And that example 7.6.
हाँ हाँ हाँ, एग्जैक्टली. ठीक है, देन आई विल क्लोज.
thank you, ma'am.
Okay,
Thank you.
thank you everyone. Thank you.